Let G be simple. At least 2. Then as a cycle, length at least k plus 1. We can give the proof on this same thing. Take the longest possible path, exactly the same way. It cannot be made any longer. Therefore, all the neighbors of y, all the vertices adjacent to y, they all must be here. How many of them are there? K of them. Take the vertex in this, which is neighbor of y, and which is as much to the left as possible. Okay? Choose one which is the leftmost among all the vertices that are neighbors of y. How much would you have to go? Because y has at least k neighbors, at least k. Therefore, there would be at least v vertices that you would be, at least k vertices that you would be traversing along with y. That gets you k plus 1 vertices, and that forms a cycle. So it's a cycle whose length is at least k plus 1. Why does this fail? In case k is equal to 1, what happens when k is equal to 1? I cannot be sure, because there is no cycle of length 2. For a simple graph, there is no cycle of length 2. If k is 1, it could just be like this. Then there is no cycle. Okay? So that is the proof of that lemma from the. So just modify the proof of previous lemma to prove to get the proof of this lemma. Just as one talks of longest path, one can talk of longest trail, longest possible trail. The point I am making is there are two types of trails in a graph. Trail by definition does not repeat an edge. It can repeat a vertex but cannot repeat an edge. This is what one would call an open trail, because it begins at some vertex and ends at some other vertex. So it's called open. As opposed to that, you could have a closed trail. Closed trail is that is closed. Okay? Because you started at this vertex and came back to the same vertex. So the lemma we want to prove, it asserts that if you have an even graph, connected graph, with all vertices of even degree, take longest possible trail in this graph. What is longest possible? That just means that you cannot add any more edge. Take is a closed trail. In that case, I got an open trail because there are vertices of odd degree. Yeah, the point is, if a trail is not closed, then it is open. Okay, there can be only two possibilities. Closed trail is one that starts at a vertex and comes back to the same vertex. Proof. Suppose T is a maximum. That begins suppose y is not equal to x. Y is equal to x, then that's what we call a closed trail. See, for a trail, even an open trail, you begin at a vertex, end at a vertex. Except for a vertex where you begin and for a vertex where you end. At all the other vertices, intermediate vertices, you would have visited them an even number of times. Once you enter that vertex and immediately you exit that vertex, enter, exit, this may happen. So there may be 50 entries and 50 exits, okay, making a total of 100 such things. But that is an even number. For every intermediate vertex, any vertex that is in the middle, it gets visited an even number of times. By visited, I mean any number of times any contribution to the degree of that is even. For every z not equal to xy, z is on an even number of edges fact which is not true only at the beginning and end. At the beginning, I step out, come back again I step out, come, etc., but I don't come back to the same vertex. Therefore, it could be something like 30 times I went out, but only 29 times I came back. Is that clear? So the last time you step out of that vertex is not matched by a corresponding coming back. All right. At x or at y, an odd number of edges but degree of y is even. Therefore, from y there is some edge that is unused. I have not used some edge, that's clear. I could not have exhausted all the edges at y. So some edge say yw then t augmented by yw on the right is a longer trail contradiction. So there is no escape from this argument. When you have each vertex of even degree, longest maximal trail that you try to construct must come back to the same vertex. It must come back to the same vertex. We are almost close to giving a second proof to Euler's theorem. So it's sort of different idea. Second proof of what is it that I do? I'm given a graph G. We are given connected G with each vertex of even degree. Construct a maximal trail in G. If this trail happens to be an Eulerian trail, Eulerian circuit, then I'm done. That's exactly what I'm looking for. I want to construct an Eulerian circuit. Let T be a maximal. We claim that T is an Eulerian circuit. What that lemma shows is T is closed. Therefore, you begin at a vertex, come back to the same vertex. By the lemma, T is closed. See, we start at X and end at X. If T doesn't really account for all the edges, then there must be some edge which is not used by T, which is not there on T. Why did that happen? If, suppose, so this edge is not there. This edge is not there on T. Why is it? But the graph is connected. The graph is connected. Therefore, you just cannot. This cannot be in different component. That means from this there must be some path leading to T. This whole thing is T. At a vertex V, I can then take the first such vertex so that means there is some vertex at which I have some unused edge. So what that means is, thus on T we have a vertex V with an unused say V to V prime. How could that happen? I can now orient this whole thing so that instead of beginning at this vertex, I can begin at V. When you have a closed situation, it really does not matter where you start. That's irrelevant. I could have begun this whole thing at V, come back at V. Okay? Make a new trail. that starts and ends, say T prime, obtained from T. But T prime is clearly not the longest, that's clear, because I could have added that extra edge. That means T prime is not really longest. Since T prime augmented by V prime is longer than we get a contradiction. Why did this contradiction arise? This contradiction arose because we assumed that there is an edge like that sticking, which has nothing to do with the trail. So all the edges have been covered on that trail. So this is sort of a stronger assertion. Any maximal trail in a connected graph with even degree, E is an Eulerian circuit. Is an Eulerian circuit. Euler's theorem has many other consequences. Some of these are entered as exercises in West book. For example, if you take a graph in which not all vertices have even degree, then the number of odd vertices, with odd degree is an even number. Suppose I have exactly two odd vertices. Suppose I have exactly two vertices whose degree is odd. Then of course I cannot have an Eulerian circuit. Can I have an Eulerian trail which starts from this odd vertex okay, something like this. Can I have, so all the other vertices are even, this vertex is odd, that vertex is odd. Can we have a trail that covers all the edges, an Eulerian trail, which begins at this odd vertex and ends at that odd vertex? Sorry? Number of odd vertices is always even. Yeah. Add one more edge. That's exactly what needs to be done. So there is a ingenuity in this whole thing. This and this, you make them adjacent by add an extra edge there. The degree of this vertex and this vertex, they were the only odd vertices in this graph. Make it an even degree graph by adding extra edge, which was, the proof really goes through even if the situation here. I want to make this clear. Still this vertex and this vertex are odd vertices. Is that clear? They are odd vertices. If they are odd vertices, join them by adding an extra edge like this. Multiple edges are perfectly all right. By doing this, this is connected and each vertex has even degree. Therefore, this has an Eulerian circuit. Because it has once you have an Eulerian circuit, you can begin at any vertex and end at the same vertex. So I could begin at this vertex and end at this vertex. I can in fact, just think about this, manipulate this so that this becomes the last edge there. This will become the last edge. Then conveniently I can remove that edge. Therefore I get an Eulerian trail. Okay. This is generalizable. Suppose I have as many as 10 vertices of odd degree. Then I can pair them up. I can pair up vertices of odd degree. 5 pairs. I can, so if I have 10 vertices of odd degree, I pair them up add extra edge exactly. So you'll have to add 5 extra edges. By doing that, each vertex will have an even degree. Then what is it that you'll do? You will obtain an Eulerian circuit. If you remove these new edges that you added, which you have to, because these edges are not there in the original graph, they have to be removed. This is as good as taking a pair of scissors in one's hand. You take pair of scissors and cut. It's like a thread that is being cut. If a thread is cut, how many cuts will you have to give? 5 cuts again, and that will break it into 5 parts. So a graph in which there are as many as 2k vertices of odd degree, the edge set, you can actually write this consisting of trails, k open trails. You can write it as a union of k open trails. The entire edge set can be covered by using k open trails. So these are all consequences of Euler's main theorem. There are ingenuity. This is ingenuity. Adding extra edges or just for convenience is the ingenuity involved in the proof. Okay. Okay. Some more things. Okay, this is a formula that we obtained earlier. 2 times the number of edges. Most basic formula. How does this follow? This is clear. Because each summand there is greater than or equal to delta G, and number of summands is equal to n. So n times delta of G is less than or equal to 2 times Ag. Whereas each summand there is less than or equal to capital delta G. Therefore, this total sum is less than or equal to capital delta G multiplied by n. Therefore, that obtains this. Okay. In case you have a graph which is k regular, recall the definition of a k regular graph. It's a simple graph in which each vertex has degree k. Okay. Then the number of edges in case of regular graph, small delta is equal to capital delta. Therefore, there is a squeezing that will happen. Small delta equal to capital delta, both of which are equal to k. They are equal to k. They all have the same degree. And then E of G will be in particular, what that means is if n and k are both odd numbers, you cannot have a k regular graph on n vertices. So there is no 3 regular graph on 7 vertices. It is not possible. Okay. One cannot just think of constructing all. You cannot just randomly throw in numbers. That is not possible. That does not exist. Okay, there is something I would like to ask you to do as an exercise. Peterson graph, something that we defined yesterday. There are 5 cycles in Peterson graph, of course. Find out the number of 5 cycles in Peterson graph. how many. It's not that there are only 2 phi cycles, that is not true. There are much larger number of phi cycles in Peterson graph. Are there 6 cycles in Peterson graph? Are there 7 cycles in Peterson graph? Are there 8 cycles, 9 cycles, 10 cycles? Okay, so these are the questions pertaining to Peterson graph. This should be doable. Sit down. For example, I can tell you that there are no 7 cycles in Peterson graph. Peterson graph has no 7 cycles, but it does have 6 cycles, 8 cycles, 9 cycles, no 10 cycle. There is no 10 cycle, but it does have cycles of length 6, 8 and 9. Out of these, how many are what we call induced? So cycle will be called induced cycle if there is an edge like this, which I have not drawn, then this is not an induced phi cycle. It is a phi cycle in the graph, that is fine, but it's not an induced phi cycle. Okay? Equivalently, what they call chord of that cycle. It's a chord of that cycle. For example, in case of Peterson graph, phi cycles are induced. Phi cycles are induced. That follows from what we said yesterday. Peterson graph is a graph with girth 5. It is a graph with girth 5. If there is a chord like this, then there will be a 4 cycle, which is not true. There are no 4 cycles in Peterson graph. Okay? So all 5 cycles are induced. Similarly, if there is a 6 cycle, it will also be induced. Okay? Whereas 8 and 9 cycles are not quite induced cycles. They are not induced cycles. There are edges going across and so on. But just think about it. In next class, I'll look at the answer to this question. We did define a 3-dimensional cube. So this is a definition of a cube in k dimension. The graph QK all binary k tuples Okay, let's. So the usual cube that we looked at is a 3-dimensional cube. Why? 0, 0, 0. For example, something like in 4 dimension 1, 0, 1, 1 is adjacent to 1, 1, 1, 1 because they differ at the second coordinate. They have to differ at least one coordinate because x and y are not equal. Therefore, they must differ at least one coordinate, but they should differ in only one coordinate. Something like 1, 0, 0, 1 is not adjacent to 1, 1, 1, 1. Okay. With this definition, the graph QK is a regular graph. How does that follow? I can just look at this. I take the vertex 0, 0, 0, 0. How many vertices is it adjacent to? I can 1, 0, 0, 0, 0, 1, 0. So I can keep changing one coordinate at a time, and those will be the all adjacencies. So the neighborhood of this consists of 1, 0, 0, 0, 0, 1, 0, 0. So it is and what is true for at 0, 0, 0, 0 can really be done at any vertex. There is nothing special. It's just convenience. Check this. Sorry? This notation? Unique. Oh, the exclamation. Exclamation is for unique. Okay? There exists only one. There exists a unique I such that there is clearly at least one I that has to be true because x and y are different. But what we are saying is there is exactly one I where they differ from each other. In the standard basic coding theory, this is what is called Hamming distance. This is exactly the idea of Hamming distance between two words. Given two words, so that's a slight detour. It would be good to do that. Distance between x and y. So x has the form x1, x2 up to xk. Is the cardinality of the set I such that xi is not equal to yi. So this is called the Hamming distance between those two binary words. The largest Hamming distance over k coordinate places is k. Like 0, 0, 0 and 1, 1, 1, the distance is 3. So that is what we call the Hamming distance. This is a metric, not a very interesting metric from topologist's point of view, but it is a metric. You can check that the triangle inequality is satisfied. It is a metric. So those that are at distance 1 according to that definition are the ones that are adjacent to a given vertex. Okay. There is quite a lot more to this. QK is called the hypercube graph, k-dimensional hypercube or cube. It is a bipartite graph. All QKs are bipartite in all dimensions. And there are many ways of seeing this. There's not quite number of ways of seeing that it is bipartite. One way, one easy way is, let me define this. I mean, now that we have gone this far. Weight of x this is called the Hamming weight. So the Hamming weight of something like 0, 1, 0 is just count how many places you have ones. That is the weight. Okay. So this is analog of, what's this? That is the metric and that is analog of the norm. The norm in function analysis. Okay. That's exactly, it's just that the setup is discrete here. There they're talking of continuous things. So the distance between x and y is nothing but weight of x minus y. x minus y, all the calculations done modulo 2, all the calculations done modulo 2, 0 minus 1 is equal to 1. Okay, 1 minus 1 is equal to 0, of course, and is that clear? So the distance and they actually differ at 3 places, they do. They differ at 3 places. So the distance between those two words is 3. The k-dimensional cube has as many as 2 power k vertices. It has 2 power k vertices. If you now take all the vertices whose weight is even, look at all the vertices whose weight is even, as opposed to those vertices whose weight is odd, then no two vertices whose weight is even can be adjacent to each other. Vertices with even weight cannot be adjacent to each other. Check this, because the way we have defined this. Two vertices that have even weight cannot be adjacent to each other. Similarly, two vertices that have odd weight cannot be adjacent to each other. Therefore, we have a bipartition. There is a bipartition for this graph. Vertices with even weight and vertices with odd weight put on the other side. So all QKs are bipartite. So as an exercise, find out how many edges are there in QK, how many cycles of length 4 are there in QK. In this case, how many cycles of length 4 are there? In case of Q3, there are as many as 6 of them. 6. This is a very visual thing. You can see that the picture there, okay? Because those are the faces, the cube that you see in 3 dimensions, actual cube, the real cube that you see. I see that there are 6 of them, okay? Do that in general. That will require more time. There is large number of 4 cycles, very large number of 4 cycles. Just see how many of them are there. And then this graph is more important for some other reason. If you take a set of order k, and look at all the subsets of this set of order k, that number is 2 power k. The total number of subsets of a set of order k, what should be called the power set of this, one can make a natural association of a subset with a tuple, with a k tuple. For example, with k equal to 4, 1, 0, 1, 1 actually corresponds to the subset 1, 3, 4. Wherever you have a 0, you omit that number. You just omit that number. Okay? So something like 1, 2, 3, 4. This corresponds to something like an empty set corresponds to. Okay? So there is a bijection, a natural bijection between the set of vertices of Qk and this lattice of the Boolean lattice consisting of all subsets of a set of order k. This can be ordered by inclusion. The standard order on the Boolean lattice is by inclusion. Two subsets are ordered by inclusion. And what would be the corresponding adjacency there? Something like a subset and some other subset. These are adjacent to each other. If one is contained in the other, or that is contained in this, but this adds only one element. So this is what is in the standard lattice theory, what they call this as a cover. This is what is called cover. The bigger set covers the smaller set. Okay? Bigger set is obtained by adding exactly one element to the smaller set. Okay? So for reasons that are connected, that connect this with other parts of mathematics, so one can draw the Boolean lattice, and this is what is called the Hasse diagram. I'll dwell on this little bit more, but think about this. As I said in the very first lecture, why some graphs are more important than others? It's because of such kinds of reasons. Okay, because they are more connected. They are more connected with other branches of mathematics. Okay, so that is for the cube graph. One wants to say what minimum degree will force the graph to be connected. G be a simple graph. This is quite simple proof. If G is not connected, then what will happen? Then it has components. Then it has components, at least two components. Let X be degree of X is at least implies that component containing X has how many vertices? It has at least those many vertices. So it is like this. X is adjacent to all these. So they all have to be in the same component, and also X. So it has at least 1 plus vertices. If I have two components or more, each one will have n plus 1 upon 2 or more vertices. That means the total will blow up to more than n plus 1 or more contradiction. That's clearly a contradiction. Is it clear? Each component, if each component has to have at least n plus 1 upon 2 vertices, you have no choice but to make the graph connected. Okay, because if one component consumes so many vertices, then the other component will have less left with it, only n minus 1 upon 2, which is not true. If each one has so many, if then n of G contradiction. So whenever such kinds of theorems are proved, one should really ask the question, is it really required? Do I really need the minimum degree to be? Basically, it's clear that larger the minimum degree, more are the chances that the graph will be connected. Is that clear? Complete graph is connected because it is very high degree. Thing is, you don't really need this. For example, if you take a path or even cycle or a path, the minimum degree is quite low. What is delta of G? and still it is connected. Okay, so that condition given in that theorem is only a sufficient condition. It is not necessary. It is not at all necessary. Not at all, in fact. You can really have delta of G very small. But on the other hand, the condition given there, one could ask the question, can I really lower this to n minus 3 upon 2? Why not? Or even something. Answer is no. Look at this. I mean, so this is the constructor. Yeah, what is this saying? Suppose you have a graph. Suppose n is even. If n is even, then make two parts in which each has n upon 2 vertices. Take a complete graph on this. Complete graph on this. What would be the degree? The degree would be n minus 2 upon 2, which is which is less than this, which is less than this number, okay? And it is not connected. This graph is not connected, though it has quite a high degree. So if I just lower this to, instead of n minus 1 upon 2, if the numerator gets slightly lowered, the theorem is not true, okay? This, by the way, is the ceiling function, okay? So what is meant by that? The ceiling function of 3.5 is 4. Smallest integer greater than or equal to the given number. That is what is called the floor. Largest integer less than or equal to the given number. If your number happens to be an integer itself, then the floor and ceil are equal. Okay, next time we will begin with a similar theorem of this kind. This is a very famous theorem called Turan's theorem. You want to have a simple graph in which you have no triangles at all. There are no triangles in that graph, and want to have largest possible number of edges. One way of doing this, there are no triangles in a bipartite graph. If you take a bipartite graph, there are no triangles. Okay. So you can sort of try to construct a bipartite graph, and because I want to have the maximum number of edges, I can take a complete bipartite graph on this. So draw all possible edges and then do this in such a way that you have, when would I get largest number of edges? If I sort of equally divide this, is that clear? Yeah, this is a purely elementary calculus problem. Okay, when the sum of two numbers is given, when is the product maximized? The product is maximized if the two numbers are about equal. If the two numbers are about equal. If x plus y is fixed, xy is maximized if x is equal to y. Okay. Yeah. Rectangle with fixed perimeter, the area is largest if it is a square. Okay. So that is what Turan's theorem is claiming, that the maximum is obtained if you take a complete bipartite graph in which you have equal. So this has to be proved. It has to be proved that that has the largest number of edges. Okay, so that is what Turan's theorem is saying. So that's what we'll do next time. Then we have to look at what kinds of degrees can occur as degrees of vertices of a graph. This is what is called degree sequence. Degree sequence for a graph. Just because I throw in some numbers, we saw it there. There is no graph. There is no simple graph on 7 vertices in which all the degrees are 3, 3, 3, 3. Cannot be done. Just because you have some numbers in your mind doesn't mean you can construct that graph. When can I say that I can give an affirmative answer? There are two ways of answering this. One is a recursive way. This is called the Havel-Hakimi theorem, which is what we'll do. So what is the recursion? When you have one question, you translate it into something else and try to answer that question. So question number 2. So from question number 1 you go to question number 2. So from question number 2 you go to question number 3, etc. So this is what Havel-Hakimi theorem does. But there is a pure graph theoretic formulation, that is what is called the Erdos-Galai theorem. Fortunately, for those who find it difficult, we don't have proof of Erdos-Galai theorem. We would have proof of Havel-Hakimi, but no proof of Erdos-Galai. Those of you who want to read things can do that. Okay. So see you next class, which will be sometime in September, not in August. Yeah.